Hello and welcome back to another episode of Weather or Not. I'm your host, Frank Gargione, joined alongside me by forecaster Jonathan Domow, except he actually will not be forecasting the show because we will be on spring break.
That's right, Frank. I'll be in Houston, Texas. I'm very excited. It's my first time in the great state of Texas. Really excited to do some exploring and just seeing what there is out there. Frank, where are you going for spring break?
I'm actually heading down to Siesta Key, Florida. I'm hoping that the weather stays nice. As of right now, it looks like we'll be in the 80s, and I'm really looking forward to heading down to the beach.
That's awesome.
Since he will not be forecasting, we have extra features produced by myself, Jonathan, and Rebecca, along with an almanac, and of course, the quiz question and the quiz answer. Without further ado, enjoy the show.
If you've driven anywhere across Pennsylvania in late winter, you've definitely felt it. That sudden jolt as your car hits yet another pothole. It seems like roads fall apart overnight this time of year, but while pothole season may feel random to drivers, it's actually driven by a very specific weather pattern that dominates February and March, the freeze-thaw cycle. A freeze-thaw cycle happens when temperatures rise above freezing during the day, then drop back below freezing at night. And here in Pennsylvania, late winter is prime time for that pattern. Sun angles are getting higher and afternoons are warming, but nights are still cold enough to freeze. That constant back and forth across the freezing point is exactly what roads do not handle well. It begins when water seeps into roads. Even strong asphalt and concrete aren't perfectly solid. They contain tiny cracks and pores. And when snow melts or rain falls, water seeps into those small openings in the pavement. Then temperatures dip below freezing. As water freezes, it expands about 9%. That expansion pushes outward on the surrounding pavement, worsening the cracks. The next day, temperatures rise again. The ice melts back into water, which can now flow deeper into the newly enlarged gaps. Then it freezes again. Each cycle acts like a wedge, prying the pavement apart bit by bit. Over days or weeks of a repeated freeze-thaw, the surface layer weakens and separates from the road below. Eventually, when a car or truck passes over that weakened spot, the pavement collapses, and a pothole forms. That's why potholes seem to appear overnight after a stretch of fluctuating temperatures. The damage has actually been building invisibly beneath the surface, until traffic exposes it. Pennsylvania is especially vulnerable to potholes for a few reasons. First, our climate sits right near the freezing line in winter. We frequently bounce above and below 32 degrees, creating ideal freeze-thaw conditions. Farther north, temperatures stay frozen longer. Farther south, they stay mostly above freezing. But here, we get the worst of both worlds. Second, winter precipitation adds constant moisture. Snowmelt, rain, and slush supplying the water needed to drive the process. And finally, heavy traffic accelerates the collapse. Once pavement has been weakened by freeze-thaw cycles, the repeated weight of vehicles finishes the job. The good news is that road crews actually plan around the science of potholes. In winter, when temperatures are still fluctuating above and below freezing, it is difficult to make permanent road repairs. Asphalt used to fill potholes needs warm, dry conditions to properly bond with the surrounding pavement. If the material is placed when the ground is frozen or wet, it won't stick well and can quickly break apart again. That's why many pothole repairs you see in the winter are temporary fixes. Maintenance crews often use something called cold patch asphalt, a material designed to be applied even when temperatures are low. Workers fill the hole, compact the material, and smooth the surface so that cars can pass safely. These quick repairs help prevent the pothole from getting larger and reduce damage to vehicles, but they aren't meant to last forever. Once spring arrives and temperatures stay consistently above freezing, road crews can begin permanent repairs. At that point, workers typically remove the damaged pavement around the pothole, cut clean edges in the surrounding asphalt, and fill the space with hot mix asphalt. This heated material bonds much more effectively with the existing road surface and is compacted using heavy equipment to create a durable repair. Sometimes crews will repair individual potholes, but in areas with widespread damage, transportation departments may choose to repave entire sections of roadway instead. This prevents new potholes from forming in nearby weakened pavement. Of course, with thousands of miles of roads across Pennsylvania, road crews have to constantly prioritize the worst damage first. Freeze-thaw cycles can create potholes faster than crews can repair them, especially during winters with frequent temperature swings. So if you see workers out filling potholes in late winter, they're often fighting a temporary battle against the weather, keeping roads safe until conditions finally allow for long-lasting repairs in the spring. For Whether or Not, I'm Rebecca Newell.
In honor of spring break, I'll be taking a break from the forecast to talk about something a little bit closer to home, the history of Penn State. Penn State's story begins all the way back in 1855 when the school was founded as the Farmers High School of Pennsylvania. At the time, the goal was simple: provide practical education for the people of Pennsylvania, especially in agriculture and science. The campus was built right here in the middle of Pennsylvania farmland, which is why State College is still surrounded by rolling fields and forests today. Just a few years later, in 1862, the school became a part of something much bigger. The United States passed the Morrill Land Grant Act, which gave federal land to states so they could fund universities focused on agriculture, engineering, and practical sciences. Penn State became Pennsylvania's land-grant university. That decision shaped the university we know today. It meant Penn State would focus not just on teaching, but also research and service to the public. Over the next several decades, the school grew rapidly. In 1874, the first graduating class walked across the stage. There were only 11 students. Compare that to today, where Penn State graduates thousands of students every year across multiple campuses. The name of the school also changed several times as it evolved. It became the Pennsylvania State College in 1874, reflecting its expanding academic programs. Then in 1953, it officially became the Pennsylvania State University, recognizing its role as a major research university. Throughout the 20th century, Penn State continued to expand. New colleges were created, research programs exploded, and the campus grew into a massive university that we see today. Beaver Stadium, for example, started as a small 500-person seat field in 1909 before eventually becoming one of the largest stadiums in the world with over 107,000 seats. Penn State also developed a strong reputation in science and research. Fields like meteorology, material science, engineering, and atmospheric science became nationally recognized programs. The College of Earth and Mineral Sciences, where many meteorology students study today, has become one of the top programs of its kind in the country. And of course, Penn State is known for its traditions. The Nittany Lion mascot dates back to 1904 when a Penn State baseball player said the team would defeat the Princeton's Tiger with a stronger Pennsylvania symbol. The name comes from Mount Nittany, the ridge that overlooks the campus. Another tradition that shows the spirit of Penn State is Thon, the world's largest student-run philanthropy event. Every year, students raise millions of dollars to fight pediatric cancer, showing how the Penn State community extends far beyond academics. Today, Penn State serves more than 90,000 students across its campuses and has alumni all over the world. What started as a small agricultural school in Pennsylvania has grown into a global research university. But even with all that growth, some things remain the same. The rolling hills around campus, the changing seasons in Happy Valley, and the sense of community that brings students together every year. So the next time you walk across Old Main or watch a game in Beaver Stadium, remember that you are standing on more than 170 years of Penn State history. For Whether or Not, I'm Jonathan Domow.
Have you ever looked out your window during a tense thunderstorm and saw a huge flash of lightning and thought, how in the world does that happen?
Lightning is one of nature's most breathtaking but dangerous phenomena that lights up the skies during thunderstorms. Across a single year, the world sees over 2 billion lightning strikes, with just 25 million of them being cloud to ground here in the United States. In just a fraction of a second, a lightning bolt can heat the surrounding air to nearly 50,000 degrees Fahrenheit, about 5 times hotter than the surface of the sun. That intense burst of heat causes the air to rapidly expand, which is what creates the thunder we hear after the flash. But how do we even get to see the lightning and hear the thunder in the first place? Inside a growing thunderstorm, updrafts transport small liquid water droplets from the lower regions of the storm to heights between 35,000 and 70,000 feet, which is miles above the freezing level. Meanwhile, downdrafts transport hail and ice from the frozen upper regions of the storm. When these collide, the water droplets freeze and release heat. This heat in turn keeps the surface of the hail and ice slightly warmer than their surrounding environment, and a soft hail or grapple forms. As these particles move through the storm, they frequently collide with one another. During these collisions, something important happens. Electrons are transferred between the particles. The lighter ice crystals usually lose electrons and become positively charged, while the heavier grapple particles gain electrons and become negatively charged. Because the storm's updraft carries the lighter ice crystals upward, the top of the thunderstorm becomes positively charged. At the same time, the heavier grapple particles fall or remain suspended in the lower part of the cloud, creating a negatively charged region near the bottom of the storm. Over time, this separation of charge creates a very strong electrical field inside the storm. The atmosphere normally acts as an insulator, preventing the positive and negative charges from easily bouncing out. But eventually, the electrical difference becomes too strong for the air to hold back. When that happens, the atmosphere releases that built-up energy in the form of lightning, a massive electrical discharge that balances the difference between those charged regions. Sometimes, the lightning stays within the cloud itself, which meteorologists call intra-cloud lightning. Other times, the electrical discharge travels between the cloud and the ground. When that happens, the negative charge at the bottom of the cloud pulls positive charge upward from the ground, often through tall objects like trees or buildings. When the connection is finally made, a powerful electrical current surges through the channel of the air. That bright flash is the lightning that we see. After the initial stroke, if enough charge is left over, additional lightning strokes will use the same channel, giving the bolt its flickering appearance. The thunder that follows comes from the air around the lightning bolt heating up extremely rapidly and expanding outward as a shockwave. Florida is known as one of the lightning capitals of the United States, and that's largely because of the state's unique geography. Surrounded by warm water on both sides, sea breezes from the Atlantic Ocean and the Gulf of America often move inland during the afternoon. When those breezes collide over the peninsula, they force warm, humid air upward, helping thunderstorms grow quickly. Those storms are extremely efficient at producing lightning and are fairly common, which is why Florida regularly sees some of the highest lightning strike densities in the country, especially during the summer months. Unfortunately, lightning also can be deadly. Over the last 30 years, the United States has averaged 51 lightning fatalities per year. Only about 10% of people struck by lightning are actually killed. The other 90% must cope with varying degrees of discomfort and disability, sometimes for the rest of their lives. Typically, the vast majority of lightning victims each year are male. In 261 instances from 2006 to 2013, 81% of lightning fatalities were male and 19% were female. So the next time you see lightning during a thunderstorm, make sure to stay weather aware and remember, it's the atmosphere balancing electricity after millions of tiny ice particle collisions inside of a storm cloud. For Weather or Not, I'm Frank Gargione.
And the answer is B, 45.6 degrees, and we've been way above that number in State College as of recent. Now, speaking of temperatures, what are the average temperatures in March in Houston and Siesta Key?
That's a great question, Frank. In Houston, Texas, it's 73 degrees, and in Siesta Key, Florida, 78 degrees. Much different than here in State College.
Yes, it is, and I'm really looking forward for that weather. Join us next week for our regular show format and another edition of Weather or Not. Have a good one.